Previously in this course, we've been engaged in the field of electrostatics, where electric charges have been collected in certain regions of space and, for the most part, remain there at rest. Like in the case of the Van de Graaff generator, for example. If electric charges did move, as in the case of getting an electric shock, their motion was brief rather than continuous. But in this unit and several that follow, we'll be investigating electrodynamic situations, like electric circuits, where electric charges are in a continuous state of motion. We are now leaving the field of electrostatics, where charges remained at rest, and entering the field of electrodynamics, where charges are in continuous motion. So how do we describe moving charges? We do so with the concept of electric current. In order to describe electrodynamic quantities like electric current, a water analogy is particularly useful. Not only is water a substance we can see, it is perhaps more importantly a substance whose motion we already know something about. So let's see what Bongo has to say here in this slide. Okay, he suggests that if water current is simply the rate at which water molecules flow in a pipe, then electric current can be thought of as the rate at which charge flows in a wire. So here is Bongo, this uptight, easily perturbed, one-eared rabbit that you've all come to know in this course. And he has a pet peeve regarding the use of the word electric current, which I've given him permission to share with you. So he says, don't be an ignoramus and speak of current flow. It's charge, not current, that flows. So to be technically correct, current does not flow. Current exists in a wire, for example. It's only charge that flows. So how do we define electric current? Well, qualitatively speaking, we define electric current to be the rate at which net electric charge flows through a surface that is perpendicular to the direction the charges move. So if you look in this first simulation, we see that we have a lot of red charges, each one having a charge of magnitude Q. And when these charges are in motion, you will notice that they move in a direction that is perpendicular to this blue cross-sectional surface of area A. Now, in the second simulation I'm showing you here, okay, you see what happens when charge, that is electrons, move in a wire. Okay, you see that the red metallic nuclei are relatively fixed in place, okay, but that the electrons, which have a somewhat random chaotic motion, generally move to the right in the wire. While any given charge may have velocity components in 3 dimensions, okay, although in this simulation I can only show them to you in 2, it's only the component of the velocity that is perpendicular to this red cross section I'm showing you here. It's only that component of velocity, okay, that counts in determining the electric current. Okay, so if you consider this red cross section, you were to count, okay, the amount of charge, okay, in the form of these electrons flowing past it per unit time, we would have a measure of the electric current in the wire. So we've just stated that electric current, which we will symbolize with the letter I, capital I, represents the rate at which the electric charge flows past a given cross-section per unit time. So this is not our first rodeo dealing with this concept of a rate in physics. For example, we know that speed is the rate at which distance gets covered and is thus calculated, okay, as a measure of distance divided by time. Similarly, acceleration is the rate at which velocity changes, calculated as a change in velocity divided by time. Power, for example, is the rate at which work gets done or the rate at which energy gets transformed. That is work or energy divided by time. So in a similar fashion, we would expect that if electric current is the rate at which charge flows past a given cross-section, we would expect to calculate the average current, okay, as a measure of the amount of charge flowing past that given cross-section, okay, delta Q, divided by the time it takes for that charge to flow past the cross-section, delta T. Now, notice that when speaking of average current, we're talking about the amount of charge flowing past a given cross-section per time interval. Okay, think back to our unit on kinematics when we distinguished between average speed and instantaneous speed. In calculating our average speed, let's say for your trip to school, okay, you came up with a single value for speed describing your entire trip by taking the total distance of your trip and dividing by the total time. Okay, but that average value that you calculated told you nothing about the real speed you were traveling at any given point during your trip, like when you were stopped at a red light, for example. So in a similar way, the average current over a time interval tells you nothing about the rate at which charge flows past a given cross-section at any single point in time. As you might expect, okay, to do this, okay, to find the value of current at any single point in time, you would need to take the limit of the average current, okay, over successively smaller time intervals, okay, until the time interval was so small as to represent a single point in time. Okay, in the language of calculus, this amounts to taking the first derivative of charge with respect to time. So as we can see in the simulation here, okay, if you look at the motion of individual charges, okay, as they travel past that cross-sectional area A, okay, you see that the rate at which they travel past that cross-section is not constant in time. It changes, okay, due to the rather complicated motion of those electric charges. So for such situations where the rate of charge flow is not constant in time, we would need to calculate the instantaneous rather than the average current. Okay, but we will say that for nearly all of the electrodynamic situations involving charge flow in this class, for nearly all of them, okay, we will be dealing with what we call a steady state situation, where the current is constant in time, such that the instantaneous current at any single point in time will have exactly the same value as the average current over an extended time interval. So think of this as being analogous to the situation we dealt with in mechanics involving constant acceleration. Okay, when we looked at almost every situation we dealt with in mechanics, we said the acceleration was constant, in which case the average acceleration over a time interval, okay, had the same value as the instantaneous acceleration at any single point in time. So, for example, the case of a falling body, we said the acceleration was always a constant 9.8 meters per second squared, okay, when we're talking about a falling body falling near the surface of the Earth, in which case for the entire motion problem, we would consider that average acceleration and instantaneous acceleration to be the same, since it was always a constant. So it should be no surprise that with a new physical quantity comes a new unit. The SI unit used to measure electric current is the ampere, sometimes called an amp for short. And 1 ampere is defined to be 1 coulomb per second. That is 1 coulomb of charge flowing past a given cross section, okay, per second. Symbolically, we can write the ampere with a capital A, okay, and of course Coulomb is represented with a capital C and second with an S. So 1 ampere is 1 coulomb per second. Turns out there are different types of electric current because charge can move in different ways in a conductor, in a wire. The first type of electric current that we'll discuss is what we call direct current, or DC. For this type of current, charge always flows in one direction, resulting in a net motion of charge. Direct current is what you typically get with batteries, for example. When an external circuit is connected to the battery, charge in that wire is always forced to move in one direction, from one terminal of the battery to the other, resulting in a net motion of charge. The other type of current that we commonly come across in our everyday living is what we call alternating current, or AC. For this type of current, charge flows back and forth, resulting in no net motion of a charge. So this is the type of current that we typically get with a generator supplied by a power company. So whenever you stick an electrical device into an electrical outlet in your house, straight into that outlet, that wall receptacle or outlet is providing you with an alternating current that is simply forcing the electrons in your appliance to vibrate back and forth, to move back and forth. And because a charge is simply vibrating back and forth, we can say that there is no net motion to that charge. This last type of current, which we don't even include in this electrodynamic class, is what we call static discharge. This is what we saw in electrostatic situations. Here we're talking about the motion of electric charges, but we're talking about a sudden and brief transfer of charge, usually electrons, from one object, like the cloud, to another, like the ground. Unlike as with the case of AC or DC, when we talk about static discharge, the charge does not continue to flow. The flow is brief rather than continuous. So, examples of static discharge that we're very familiar with, lightning is a great example. Rubbing your shoes on a carpet and getting a shock. There is a sudden brief motion to that charge, but it is not continuous, as is the case with direct current or alternating current. All right, when we talk about electric current, that is the rate at which charge flows, there's really two types of electric current we can talk about. There's direct current, or DC, as opposed to alternating current, or AC. Now, when we talk about electrons flowing in a wire, when we're speaking of direct current, we're speaking of electrons always moving in the same direction, always flowing in one direction in the wire. As opposed to alternating current, AC, where those electrons first move one way in the wire and then move back in the opposite way. Now, they do this rather quickly. In this country, we have 60 hertz alternating current, which tells us that those electrons are really vibrating back and forth in your wire 60 times every second. Now, to show you this, the difference between DC and AC, I'm going to take our little DC AC demonstrator here, and inside of this light bulb is a rather large filament which is surrounding a tiny magnet. You'll notice that when I put it on the DC setting, because we've got electric charges moving in a magnetic field, there's going to be a force acting on it, and that force is always going to be in the same direction because the charges are always moving in the same direction. And that's why the filament appears pretty stationary once it settles down. If I put it on the AC setting, however, since those electrons are moving first one way then the other way, the force on those charges in the filament, because of the magnetic field, will first be in one direction and then in the other direction. This will cause the filament to oscillate back and forth as the force changes. So here it goes. Here's the AC setting. And you'll see that filament goes crazy as the force is not always in the same direction because the current the motion of electric charge is not always in the same direction.
So when it comes to speaking about the direction of electric current, we have this complication where it turns out that history is not our friend. Today, we know that the charge carriers in metals, okay, they're responsible for electric current, or the electrons. But when the conventions of positive and negative charge were devised a couple centuries ago by none other than Ben Franklin, it was assumed that positive charge flowed in a wire. Remember that the subatomic particles, that is the proton and the electron, did not exist at that point of time. And because we are slow to break with tradition, we continue to respect this historical convention of positive charge flow when we speak about conventional current in a circuit. Thus, conventional current is, by definition, the direction that positive charge carriers would flow in a circuit.
Let's review what we just stated in the previous slide. We can say that the direction of conventional current is the direction that positive charge carriers, that is, positive charges, flow. So you might ask, since today we know that it's really the electrons that are the charge carriers in metallic conductors, how does conventional current correlate with electron flow? Well, let's take a look at the possibilities, and we'll start by considering the simulation. In the simulation, consider this to be, for example, a wire that is connected to two terminals of a battery. And you can see in the simulation that electrons, that is negative charge carriers, move away from the negative terminal, right? Like charges repel. And that is what is really happening when you look at current in a metallic conductor. Talking about electrons flowing in the simulation away from the negative terminal to the right is completely equivalent to saying that, okay, an equal number of positive charge carriers, okay, move in the opposite direction to the left. So that's really what we're talking about when we're talking about conventional current. So to state this, okay, when electrons are moving in the opposite direction to the positive charges, we would ascribe a positive sign to the electron current. In other words, saying that a given amount of positive charges move past a given cross-section per unit time is completely equivalent to saying that the same amount of negative charge moves in the opposite direction past the cross-section in the same amount of time. These two situations are physically indistinguishable. So while we're technically not being correct, okay, when we talk about positive charge flow, okay, the value you get when you calculate the electron current, okay, is not affected in the least. Okay, but when electrons move in the same direction as positive charges, okay, then we would have to ascribe a negative sign to the electron current. Since the flow of positive and negative charges in the same direction, okay, would reduce or cancel the net charge flowing past a given cross-section per unit time. So in this slide and the next, we'll take a look at a few examples to get a better grasp on this concept of conventional current as well as electron current. So these examples will help us to see what happens when we have both positive charge carriers, negative charge carriers, or both moving in a certain situation. So in the examples below, we are asked to first determine whether there is a non-zero current, and if so, to specify the direction of the conventional current, okay, for the particular example. So in our first example, we're told that a beam of electrons moves from left to right. In other words, we have electron flow to the right. Is there a non-zero current? Yes, because there is a net flow of charge in a given direction. Saying that negative charge carriers move to the right is equivalent to saying that positive charge carriers move to the left. Therefore, the direction of the conventional current, which is the direction that positive charge carriers move, is to the left. In the second example, we're told that a beam of protons moves upwards. So yes, this does give us a non-zero current since there is a net flow of charge in a given direction. And since protons are positive charge carriers and they're moving upwards, okay, then the direction of the conventional current in this example will be upwards. So, in the next example, we're told that in a solution, positive ions move to the left and negative ions move to the right. So if this is an electrolytic solution, we can certainly say that there is a non-zero current here. Okay, let's see how. So positive ions moving to the left gives us a conventional current to the left, since, as we know, the direction of conventional current is the direction the positive charge carriers move. Remember we said that if positive charge carriers move in one direction, having negative charge carriers move in the opposite direction is completely equivalent. Okay, so long as we've got the same magnitude of charge, okay, moving per unit time in each case. So in this example, negative ions moving to the right is completely equivalent to positive charge carriers moving to the left, in which case both sources of moving charge contribute to conventional current to the left. In our next example, we're told that blood carrying both positive and negative ions of equal and opposite charge at the same velocity flows upwards through a vein in your leg. So here we have a situation where there is no net motion of charge. We have an equal amount of positive and negative charge carriers moving in the same direction in the same amount of time, okay, which would tell us that the net flow of charge is zero, in which case there is no current. And in our very last example, okay, with a metal car, okay, which has no net charge moving westward on Highway 99, we have a similar situation as the example above, where we have no net charge in motion. Okay, why? Because we've got equal amounts of positive and negative charge moving, in which case the net motion of charge is zero, okay, meaning that there is no current.
All right, so let's take a look at one more example. And in this case, we'll take a look at a quantitative example, okay, where we plug some numbers in. So in this problem, we're told that 5 coulombs of positive charge moves to the left in a circuit in a time of 2 seconds, whereas 3 coulombs of negative charge moves to the right in the circuit in the same amount of time, that is 2 seconds. Okay, what is the conventional current in the circuit? So before we start plugging in any numbers, okay, let's take a look here at our circuit, and we see here, okay, what I'm showing you with the arrow, okay, this large line represents the positive terminal of a battery, and we can see that in this case here, the conventional current, okay, represents the direction that positive charge carriers would move in the circuit. That is, positive charge carriers move away from the positive terminal, okay, of that battery. So getting back to the problem here, to figure out the current, okay, we need to figure out what is the equivalent situation, okay, for these negative charges moving. Okay, how do we translate negative charge flow into positive charge flow? So what we've been saying here is that if we have 3 coulombs of negative charge moving to the right, okay, in the circuit, that is completely equivalent to saying that we have 3 coulombs of positive charges moving in the opposite direction, that is to the left. So once we have this equivalent situation, okay, we can now calculate the conventional current, since we have everything in terms of positive charge flow. So we see here that, okay, the 5 coulombs of positive charge moving to the left with our equivalent 3 coulombs of positive charge moving to the left gives us a total of 8 coulombs of positive charge carriers moving to the left in a time of 2 seconds, okay, for a conventional current of 4 amperes to the left.
So we now have a macroscopic definition of electric current. That is the net or total charge passing a given cross-section in a wire per unit time. But we would like a microscopic expression for the current, an expression that involves the motion of the charge carriers themselves. So in order to do that, we're going to derive that expression in this slide, okay, an expression for current in terms of microscopic properties. And in order to do that, we're going to consider a cylindrical section of a conducting wire. Consider this to be a right circular cylinder where we're going to introduce the following quantities. Okay, we will assume that delta x represents the length of that cylindrical section of wire. We're going to assume that A represents the cross-sectional area of that cylindrical section of wire. We're going to let Q represent the size or magnitude of one of the mobile charge carriers, okay, in that cylindrical section. So while there may be the nuclei of metallic ions, which are also charged, and as we said in a previous slide, the metallic nuclei are relatively fixed in place. So the charges we're referring to here are the mobile charge carriers, which in the case of a metallic conductor is going to be what we call these conduction electrons, these outermost electrons that are most loosely held, okay, by the atoms themselves. V sub d, that is a symbol we're going to use for the drift speed. Okay, and it represents the average speed of each of these mobile charge carriers in the direction of the current. Okay, that is along the wire. And finally, n, little n, is a symbol we use for the charge carrier density, which represents the number of charge carriers per unit volume. So we will start our derivation by figuring out what the total volume of our wire cross section is. And you can see using some very simple geometry that for a right circular cylinder, taking the cross-sectional area of the cylinder and multiplying by the length of the cylinder, in this case A times delta x, we get an expression for the total volume. From there, we can figure out the total number of charge carriers in that section of wire. Okay, since we know that little n represents the charge carrier densities, that is the number of charge carriers per unit volume, we now can multiply by the volume to get the total number of charge carriers in that section. Okay, from there, what we're really interested in is the total amount of charge in that wire section. So multiplying the total number of charge carriers by the charge of each charge carrier, okay, we get this expression for the total charge in that cylindrical section of wire. So Na delta x is the total number of charge carriers. Multiply that by the charge of any given charge carrier Q. We now have an expression for the total charge, okay, of all the charge carriers in that wire section. Next, we want to get an expression for the time it takes for any given charge carrier to travel the length of that wire section. So just using some very simple kinematics, assuming that each of these charge carriers, which represents an average speed, okay, so which we're considering to be constant here, looking at the case for uniform motion where the speed is constant, we can say the time it takes for any charge carrier to move the length of the wire is simply the length of the wire divided by that constant speed of each charge carrier, which we said is simply the drift speed, okay, V sub d. So now we're in a position to use these microscopic variables to get an expression for the current. And remember, we said that the steady state electric current, where we're assuming that these charge carriers are moving at a constant speed, is simply the total charge passing a given cross-section per unit time. We take our expression for total charge, that is NAQ delta X, divided by our microscopic expression for total time. And when we do a little bit of canceling common factors here, we notice the delta X's cancel. We end up with this expression for current, a microscopic expression for current expressed in terms of microscopic quantities here. So N times A times Q times V sub D, the drift speed. So let's use this microscopic model for electric current that we developed on the previous slide and apply it to a specific example, really a specific type of metal, and we'll consider copper because copper is a very common metal used in electronic circuitry, used in wiring. And we're going to use this specific metal to get an order of magnitude estimate for the drift speed. How fast these mobile charge carriers, really the electrons in copper atoms, are moving, when we talk about an electric current being set up in a copper conductor. So in reading the problem here, we're given a copper wire having a cross-sectional area of 10 to the minus 6 square meters. It carries a current of 5 amps. The charge carriers in copper are electrons, as is the case with all metallic conductors. And each copper atom contributes on average 1.3 free electrons. So while a given copper atom has many electrons, not all of those electrons are really free to actually move and leave the atom entirely. It's really only the outermost valence electrons, those most loosely held electrons, that have the possibility of becoming our mobile charge carriers. And it's very simply think about what Coulomb's law tells you. You have a metallic nucleus which is positively charged, exerting a force on the electrons in the atom. Well, certainly the force is weakest on those outermost electrons because they're furthest away from the nucleus, and those outermost electrons are also experiencing what we call the shielding effect, that is repulsion from inner shell electrons. So those are the most weakly held electrons. And really, on average, we're saying only about 1.3 electrons in a given copper atom is actually free to escape that atom entirely and move freely, contributing to an electronic current that we're talking about in this problem. We're given the density of copper in this problem here, and we're asked to find the drift speed of these electrons. And as a follow-up, we're asked to comment on the order of magnitude of this drift speed. So think about the model that we used in the previous slide and the expression that we derived for current in terms of these microscopic properties, like drift speed. So since we're asked to find the drift speed here, all we're going to do is take our expression for the current here and solve it for drift speed. Remember previous slide, that average current went like NAQV. In this case, we just solve it for the drift speed V. Notice here that the current and the cross-sectional area are given to us, so what we really need to do in this problem is find the charge carrier density N. That's our biggest challenge here. Q, that is the charge of a mobile charge carrier, which is simply the charge of an electron. So I'm going to start here. This does help if you've had some chemistry in your background. The number of moles of copper atoms per volume. And if you think about your understanding when you learn stoichiometry, moles and molar mass, if you take the mass divided by the molar mass, let's say mass in grams divided by the molar mass, which represents how many grams per mole. So grams divided by grams per mole gives you moles. So taking the mass dividing by the molar mass gives us a measure of the number of moles of copper atoms we have in this cross section, per unit volume. Well, as you can see here, the mass divided by the volume is simply the density. Okay, so this expression here becomes the density over the molar mass. So plugging in the numerical values we have, the density is 8,920 kilograms per cubic meter. The molar mass can be looked up from periodic table, okay, about 63 grams per mole, or in SI MKS units, 0.063 kilograms per mole. We do the number crunching and we get this value of 1.4 times 10 to the 5th moles per cubic meter. So what we're really interested in is the number of mobile charge carriers per unit volume. That's N. We're getting there. So let's go from moles of copper atoms to number of copper atoms per volume. And we can get that simply by multiplying the number of moles per cubic meter by Avogadro's number. Okay, that tells us how many atoms there are in a mole. And this gives us now how many atoms, how many copper atoms we have in this cross section here. Okay, sorry, how many copper atoms are in a cubic meter in a given volume of a sample of copper. So from there we can now use the fact that each atom contributes 1.3 free electrons. Okay, we can then say the charge carrier electron density. Okay, if we've got 8.5 times 10 to the 28th atoms per cubic meter, and there's 1.3 free electrons per atom, simply by multiplying these two numbers, we get an expression for the number of mobile charge carriers per cubic meter. That is the charge carrier density, the 1.1 times 10 to the 29th. So now that we know N, it's simply a matter of plugging into our handy-dandy formula here for drift speed. The current we set as 5 amps. Plug in our value for N. Cross-sectional area is given to us, and it's the electrons that are the charge carriers here. And we know the charge of an electron, 1.6 times 10 to the minus 19th coulombs. We do the number crunching here, and we find that the drift speed, okay, this is the average speed with which the electrons move down a copper wire at room temperature, is about 0.28 millimeters per second. Think about it, 0.28 millimeters per second. You know how small a millimeter is. Okay, so when we're asked to comment on the drift speed of electrons in a copper wire, and typically in most metallic conductors, you see here it's extremely small. So this may be a surprise to you, where you think of these very small electrons as moving quite fast. When we're talking about an electron current, okay, the average rate at which they're moving, down a metallic conductor is not fast at all. According to our friend here, okay, it says, how can the drift speed of electrons be so small? If you think about it, when you turn on a light switch, the light comes on almost instantaneously. It comes on immediately, not several thousand seconds later. Okay, well, okay, dude's friend here answers the question for him. Okay, he says that you're confused because you're failing to distinguish between the speed of the electrons in the wire and the speed of the electrical signal in the wire. The electrons travel slowly, that's true, but the signal that tells the electrons to move, okay, the signal that exists in the form of the electric field, that travels at nearly the speed of light. So if we look at the process of turning on a light switch, let's take a look at what happens. Okay, when the light switch is turned on, the signal in the form of an electric field travels at roughly the speed of light from the power company to the filament in the light bulb. So that signal may be traveling many, many miles, but traveling at the speed of light, okay, will reach the filament of that bulb nearly instantaneously. And when that signal reaches the filament of the bulb, it now tells the electrons to move. Remember, this is AC current, okay, alternating current, so it basically is pushing the electrons back and forth, causing them to vibrate back and forth. So you see that the electrons may travel very slowly, okay, but the signal that tells the electrons to move actually travels extremely fast. So I think an analogy will be very helpful here in helping us to understand the difference between electron motion, okay, okay, which we said is quite slow, versus the motion of the signal, which we said is quite fast. The wrong analogy would be the domino model, and this is a common misconception, okay, that what causes electrons in a wire to move is not what is taking place with a stack of falling dominoes. You see in the simulation here that what causes a domino to move is when it is experiencing a collision from its neighbor. One domino collides with its neighbor, that domino collides with its neighbor, and this process will cause the dominoes to move, but it's actually quite slow. This is not what is happening in the case of the electrons moving in a metallic conductor. It's a pretty good analogy for what happens in thermal conduction to explain the flow of heat, at least one type of heat flow, but it's not good to explain what is happening, okay, in terms of the electron motion in a metallic conductor. So let's take a look at a far better analogy, and that better analogy is the analogy of marching soldiers. So when you look at what the case of marching soldiers, you may have a line of soldiers. What's going to allow the soldier at the front of the line to start moving? Well, you see here in the simulation, we've got the commander at the rear of the line. Okay, so when that commander ushers a signal, okay, in this case through his bullhorn, that sound wave travels from the rear soldier all the way to the frontline soldier, well, in this case at the speed of sound. In the same way, when the light switch is turned on, the signal to tell the electrons to move in that wire, okay, travels at roughly the speed of light. So we can say that when the soldier in the front hears the sound, he or she begins to move. Okay, that soldier is not moved because a soldier behind him bangs into him, collides with him. That soldier moves as soon as that soldier receives information from the sound wave. That sound wave travels extremely fast, much faster than the speed of the soldiers themselves. So once again, this is what's going on with electrons in a typical circuit. The electron, let's say in the filament of a light bulb or an electrical appliance, okay, when the switch is turned on, that electron is receiving a signal in the form of an electric field, which travels at roughly the speed of light throughout that circuit, telling that electron to start moving.
So suppose we have a fan that is blowing on a Van de Graaff generator, blowing electrons into a classroom full of Physics 103 students. Note that depending upon where you're sitting in the classroom, the number of electrons hitting you per unit time will vary. Some students sitting directly in front of the fan are getting hit by many electrons in a 1-second time interval. Okay, while students sitting at the sides of the classroom are not getting hit by as many electrons. Up to this point, we've assumed that the amount of charge flowing past a given cross-section of wire was constant in time. While this may be a good approximation for charge flowing in a solid conductor, when we speak of charge flow in liquids, gases, or plasmas, this approximation breaks down, as we see in the case of electrons moving through the air in the Physics 103 classroom above. For such cases where the total charge flowing past a given cross-section per unit time is not constant, we invent the concept of current density.
So let's formally define this concept of current density that we qualitatively introduced in the previous slide. We will use a symbol capital J, notice with the vector symbol above it letting us know it's a vector quantity, to represent this quantity we call current density. So when we talk about the meaning or definition of current density, we can say that the magnitude of the current density is simply this ratio of current per unit area. So when we look at the current moving through a certain region of space and divide by the area of that cross-sectional area of that region of space, we now really have a measure of, okay, the current at a single point in space. This is what we call the current density. So we can take this ratio of current per area using our microscopic model for current, okay, and just plugging in our microscopic expression for current here, NAQVD, okay, dividing by the cross-sectional area, and we come up with this simple relationship. Notice here that V sub D is no longer the drift speed that we talked about previously for current, which was a scalar quantity. We now write it as a vector quantity, and we call it the drift velocity, so that it does have direction. And the direction of the current density, the direction of the drift velocity, okay, is the direction that the mobile positive charge carriers move, right? Opposite the direction of negative charge carriers, completely consistent with everything we said previously about conventional current. Okay, so current density, okay, by convention follows the same convention we use to describe conventional current. We're looking at the direction that positive charge carriers move in a medium. So just to quickly review, when do we use this concept of current density? We need it when the current is spread over an ill-defined area such that the magnitude of the current and or the direction of the current will vary from one point in space to another. So typically when we look at the current in a wire, we're assuming that the amount of charge passing a given cross-section of that wire is per unit time is the same at all points along that cross-section. But what if that were not the case? Okay, in such a case, then we would have to talk about the current density, okay, which would give you a measure of the current at a single point in space. So if you want to calculate the current given the current density, if you have an expression for the current density, okay, what we're saying here is that the current is no longer constant over the entire large cross-sectional area A. What do we have to do? We have to look at a small enough piece of that cross-section, an infinitesimally small piece of that cross-section, okay, one so small, what I'm showing you in red here, okay, having an area dA, that we can consider the current to be constant over that very small cross-section. In that case, okay, we would say that the current over that very small cross-section is just J times the cross-sectional area dA. And if we want to find the total current, okay, through the entire area we're talking about, the entire big cross-section A, well, then we simply have to sum up, okay, all of those, the current density over each infinitesimal dA, okay, to find the total current through that region of space. So we're just invoking the techniques of calculus that you've seen us do, okay, so many times in this course already, you know, up to this point in the course. So, you know, examples where the concept of current density would be useful or required, where just calculating a conventional current would cause problems for us, where it would not be accurate. You know, currents in the Earth's core. Here's a case where when you look at the motion of charges in the Earth's core due to the convection current set up, okay, the amount of charge passing a certain point in space per unit time is not constant over a big region of space. So for such a model, okay, to represent those convection currents, you'd have to talk about the current density rather than the current itself. Same thing would apply to motion of charged particles in the atmosphere, whether those charged particles are coming from the sun or some other source. You cannot assume that, okay, the amount of charge passing a large region of space per unit time would be constant, okay, in time, in which case you have to, you know, look at a much smaller region of space, okay, when you're calculating the current. Currents in chemical solutions like voltaic cells. This is becoming a huge topic in our quest for, you know, much more efficient voltaic cells to be used in transportation. currents existing in ionized gases, okay, from which stars are composed. So if you look at models for stellar formation, when you actually look at the motion of these gases in your protostars, okay, then you would be talking about using current density, okay, since the current changes with location. So pretty much in general, anytime currents are not neatly confined, okay, to a wire, okay, then very often we use the idea of current density, as we will see in some of the problems we take a look at. Even in cases where you have current in a wire, if for some reason the charge passing a given cross-section is not constant in time, okay, then you would have to invoke this idea of current density. So now that we've discussed what current is from both a macroscopic and microscopic point of view, let's address the more fundamental question, okay, and that is, what causes current in the first place?
So the question is, what causes electric current? Well, here's a case where we can use our water analogy to help us out. In the same way we can ask the question, what causes water to flow through a pipe? We say, well, there's got to be a difference in pressure across the ends of the pipe. If I had 1 million pressure units on one side of the pipe and 1 million pressure units on the other side of the pipe, we'd all agree there's a lot of pressure on the water in the pipe. But because there's no difference in pressure across the ends of the pipe, water's not going to flow. If I had 2 million pressure units on this side and only 1 million pressure units on this side of the pipe, now we have a difference in pressure across the pipe, and water will flow from the high pressure side of the pipe to the low pressure side of the pipe. This is exactly the same for the flow of electrons. If I take this spectrum tube here, and I have a very high electrical pressure that I can produce by this Van de Graaff generator, notice what is going to happen if I connect both ends of the spectrum tube to a very high electrical pressure. Let's say 50,000 volts of electrical pressure on the dome. Let me turn this on, and you'll notice that while there's a lot of electrical pressure here, there's no difference in pressure across the ends of this tube, and because there's no difference in electrical pressure, we're not actually getting charge to flow through the tube, and therefore you can't see any light in the spectrum tube. If I make a very slight adjustment, if I now have one end of the tube connected at 50,000 volts and I connect the other end of the tube at 0 volts, now all of a sudden we have a difference in electrical pressure across the tube. We now get electrons to flow through the tube. We now have electric current, as you can see by the light. So, once again, it's not electrical pressure per se that causes charge to flow or causes current. It's a difference in electrical pressure or voltage across the ends of a wire that causes current.
In this slide, we'll put the sounds into words, formally stating the conclusions that we came to in the previous demonstration. So when answering the question, what is required to make water move in a water-filled pipe, we see that it's not pressure per se, it's a difference in water pressure across the ends of the pipe that makes water move from the high pressure side to the low pressure side. In a similar fashion, when we ask the question, what is required to make charge flow in a wire, okay, we can similarly say that it is a difference in electrical pressure, that is an electric potential difference across the ends of the wire, that will make charge flow from the high pressure side to the low pressure side of the wire. So we've just said, from a macroscopic point of view, that an electric potential difference between 2 points in a conducting medium is what is required to generate or cause an electric current. We can also describe the cause of an electric current from a microscopic perspective as well. Okay, what is it that causes individual charge carriers to move in a conducting medium? Well, as we know from our discussion of electrostatics, it's electric fields that can exert forces on charge carriers. So if an electric field gets set up in a conducting medium, that electric field interacts with the charge carriers there, exerting a force on them. And since those charge carriers are mobile and are allowed to move, okay, those charge carriers move under the action of the electric field, thus producing an electric current. So in this slide, we'll take a look at an example that I think nicely illustrates what we've just been talking about, namely the cause of electric current. And I don't know if you've ever noticed this, but if you were to drive down Briggsmore Avenue in Modesto, let's say, in the wintertime, you will probably see hundreds, if not thousands, of birds sitting on the power lines. Now, these birds may be exploiting a little bit of the thermal energy generated by the current in these lines, okay, but these birds are happy, okay, they're not getting fried, okay, why not? So let's try to answer this bird's question, which is how can they safely perch on, let's say, a 100,000 volt power line without getting electrocuted? Well, let's think about what we've just been talking about. Okay, the answer has nothing to do with insulation, but everything to do with the cause of electric current that we've just discussed. It's not electric potential or voltage that is the problem, right? Okay, it's an electric potential difference that counts. So long as these birds are standing on a single power line such that every part of their body is at the same electric potential, even if it's 100,000 volts, there is no problem. Okay, there is no current. Okay, there is no electric potential difference across the bird's body that could cause charge to flow. So you can see why these birds are happy and singing. Now, a related story, back in the 1980s, okay, and I remember this very clearly. I know this is, going back to a point in time before many of you were born, okay, but so you're not going to be able to say that you probably remember this, but I remember very clearly there was an ad campaign that was run by one of the major oil companies, Chevron. And back in the 1980s, this was a time when oil companies started to develop a very bad reputation with the public. Okay, you may recall hearing about the Exxon Valdez oil spill up in Alaska. This was going on in the mid 80s, and so oil companies were suffering from bad public perception, and they responded with TV ads that were designed to change public opinion. And there was one such ad that I remember very clearly, okay, run by Chevron, where Chevron advertised spending a lot of money to relocate a species of large wingspan birds, okay, that were building their nests atop power poles stationed in the southwestern portion of the country. Now, these birds were getting electrocuted, not like the friends you see here on the screen. They were getting electrocuted en masse. Why? Well, you think about it, because their wingspans were so large that they could end up touching two power lines simultaneously with their wings. Okay, and if these power lines happen to be at different electric potentials, okay, then an electric potential difference would exist across the body of the bird, okay, which would cause charge to flow and cause fried bird. So Chevron claimed to spend a lot of money to relocate these birds to safe habitats. And after all of these years, I can still remember the conclusion, okay, the ending line of that commercial. Okay, there was a nice voice, okay, that came on that said, "Why would an oil company spend so much money to ensure the safety of these birds?" And you know what the answer was? It was because we care. So in this slide, we'll revisit our microscopic model for electric current. Now, you may recall in a previous slide, we looked at an example where we calculated the drift speed of the mobile charge carriers, that is the electrons, in a metallic conductor, specifically for copper. So we came to the conclusion that the drift speed of these mobile charge carriers was in fact quite small. But we didn't really talk specifically about the electron motion, okay, the motion of those charge carriers in the conductor, and that's what we're going to do now. So there is a model called the Drude model for metallic conductors, not to be confused with the Dude model, okay, that describes what happens when an electric current is set up in a conducting medium. And recall what we just said on a previous slide. What is the cause of electric current? Well, on a microscopic level, we say that when an electric field gets set up in the conducting medium, that electric field can interact with the charge carriers in that medium, exerting a force on them. And because these charge carriers are mobile, that is the definition of a conductor, those charge carriers will move under the action of that force. Now, when we take a look at how do those charge carriers move, okay, this is where the Drude model comes into play. And if you take a look at this diagram on the left, okay, what I'm showing you here is the path of a given conduction electron when there is no electric field present in that conductor. Okay, so in the absence of an electric field, those electrons are moving. Even at room temperature, okay, in a conductor, those electrons are moving quite fast, on the order of about 1,000,000 meters per second. Those electrons are moving back and forth. They're colliding frequently with the fixed metallic nuclei, okay, the metallic ions, and they're bouncing off randomly, moving in all sorts of direction. Because the motion of those conduction electrons is random, there is no net motion in any preferential direction, in which case there really is no electron current. This is simply the random thermal motion, okay, caused by the fact that these electrons are at a temperature above absolute zero, okay, and the randomness happens because of the collisions they make with the metallic nuclei. So let's now take a look at what happens when you add an electric field into that conducting medium. That's a situation we have here on the right. So with an electric field present, the random thermal straight line motion of the electrons still exists. It is modified only slightly. Okay, those electrons moving at about 1,000,000 meters per second, that doesn't happen because of the electric field. That happens because of the thermal energy, really the kinetic energy that those electrons have, okay, by virtue of existing in a medium, okay, at a temperature above absolute zero. Now, if you think about it, if the metallic nuclei were not there, and you subjected an electron to an electric field, which would exert a force on it, that force would cause these electrons to accelerate, okay, and those electrons would move down the wire faster and faster and faster. Okay, their speed would end up being quite large. But because those electrons keep banging into the metallic nuclei, okay, not only slowing them down but changing their directions, okay, because of that collision frequency is quite high, those electrons will not really gain much speed or energy from the electric field, okay, because they do not have to travel far before they interact with another metallic ion. Okay, the presence of the electric field will ultimately cause those electrons to very slowly drift in a direction really opposite the electric field. Remember, the electric field tells you the direction the positive charge carriers move. So these electrons move opposite the direction of the electric field, but they move very slowly. They can never really gain enough speed because of their frequent collisions with the metallic nuclei. So you need to kind of see in this model, there's really two types of motions that we're really talking about when we talk about electron motion. There is the random thermal straight line motion, which is quite fast, okay, which we say that the velocity of these electrons are continually changing directions because of their frequent collisions with the metallic nuclei. But then there is the very slow drift speed, okay, that happens because of the electric field, okay, and these electrons can very slowly accelerate before they get stopped by another metallic nuclei. So we see here, with this very simple model, why it is that these electrons never move very fast, okay, under the action of that electric field. In fact, okay, they kind of move at a snail's pace on the order of about 1/10 of a millimeter per second.
We've said that in order to get charge to flow in a wire, you must have an electrical pressure difference, okay, or voltage difference across the ends of the wire. So it should make sense that as that voltage or electric potential difference across the ends of the wire gets bigger, as the pressure difference gets bigger, you're going to get more current, okay? That is, a current will get bigger, which means you get more charge flowing per unit time. It turns out there's another factor that's going to affect how much charge flows in a wire, okay, how fast it flows and how much of it flows. And that's this quantity of electrical resistance. The good news is that to understand, it's a little bit easier to understand than, okay, this idea of voltage. So when we talk about electrical resistance, we're really talking about a measure of how much obstruction there is to charge flowing in a wire. As charge carriers in a wire, and these for metallic conductors are the electrons, as those electrons try to move in a wire, okay, there's obstruction, okay, stuff's getting in their way. Well, what is this stuff in the case of metallic wires? It turns out that the nuclei of the atoms themselves, that is the protons and the neutrons in the nucleus, get in the way of those electrons flowing down a wire, as this simulation kind of nicely shows you here. Notice that the positive nuclei, that is the red region, okay, obviously not drawn to scale here, much smaller, but when you look at the atom here, you have that positive nuclei consisting of protons and neutrons. Those are relatively fixed in place. They may vibrate a bit, but they don't move much. But those blue electrons, those purple electrons that are actually moving from the left side of the wire to the right side of the wire, have to get around those nuclei. Those nuclei are getting in the way. Okay, they're providing a measure of obstruction to those electrons moving down the wire. And resistance, then electrical resistance, is a measure of how much obstruction there is. It turns out that some types of metals offer a lot more resistance, a lot more obstruction than other types of metals. Okay, and this is something that we'll talk about in the upcoming slides.
A physical quantity that is related to electrical resistance, okay, is this quantity we call resistivity, okay, which we symbolize with the Greek letter rho. So like electrical resistance, we can say that resistivity is a measure of how much obstruction there is to charge flow. But, okay, resistivity is a property of the material itself. Okay, it measures how difficult it is for charge carriers to move in response to an electric field. Okay, so while there are similarities between resistance and resistivity, there are some important differences between these two quantities. Okay, namely that resistance is an extensive property. Okay, it's an extensive property of the conductor. It depends upon the size and shape of the sample of matter that you have. Whereas resistivity is an intensive property of the conducting material, okay, completely independent of the size and shape. So for example, copper has a certain value of resistivity at a particular temperature. Okay, it is a property of the material we call copper. But if you had a copper piece of wire, okay, that piece of wire is going to have a certain amount of resistance, which does give you a measure of obstruction to charge flow. Okay, but the amount of resistance that that piece of copper will have will certainly depend upon the shape and the size of the copper sample.
So as you well know, anytime you introduce a new physical quantity, you must have a new unit, okay, to be able to make measurements of that physical quantity. So what is the unit that we use to measure this physical quantity we call electrical resistance? Well, let's look at this little guy for some clues. Yes, figure out it is the ohm. And in words, an ohm is defined to be a volt per ampere. 1 ohm is 1 volt per ampere. Where this definition comes from, you will know very shortly when we talk about Ohm's law. You will see that resistance is a measure of potential difference or voltage per current. That's why we have a unit volt per ampere. Symbolically, we use this capital Greek symbol omega, looks like an upside down horseshoe, to represent the ohm. So as we said, it is a volt per amp. Just for fun, and don't worry about this, this won't be on the test, you can see how many of these puns, okay, involving the ohm you can figure out. So you might want to pause the presentation at this point, and in about 5 seconds I will give you the answers. All right, I think that's about 5 seconds. So let's see how well you did. If we look at, okay, the picture in the upper left here, okay, that is what we would call a mobile ohm. The one next to that, you might have figured out, this is what we would call an ohm run. This one over here I'm showing you is what we would call the ohm stretch, okay, running along the lines of the baseball thing. And the last one in that top row is ohm sick. Okay, lower left here in the second row, every good physics student knows that's ohm work, right? Force times distance, a measure of work. The one next to that is ohmless. And here, this is probably one of the tougher ones. And in your generation, you may not be familiar with this, but this is what we would call an ohm on the range. Okay, it's an old cowboy song here, before my time too, believe it or not. And the last one over here, this is what we would call a broken ohm. So, like I said, I hope you enjoyed that, but okay, it won't be on the test. Now that we know the meaning of electrical resistance, in this slide we'll take a look at some of the factors that affect the electrical resistance in a wire. Starting with the length of the wire itself. It turns out that there is a direct relationship between the resistance of a wire and its length. I'll demonstrate this for you in the next slide, along with a second factor we'll take a look at shortly. But hopefully this would make sense to you, because as a wire gets longer, okay, this means that there are more nuclei that are obstructing the path of the electrons. In other words, longer wires would have more metallic nuclei. And remember, we said that it's those metallic nuclei that are getting in the way of the electrons being able to move from one side of the wire to the other. Longer wire, more metallic nuclei, more obstruction in general. Therefore, greater overall resistance. A second factor here is the cross-sectional area of the wire. And this may be a little bit counterintuitive, but it turns out that there's an inverse relationship between resistance and cross-sectional area. We'll demonstrate this in the next slide, along with the factor we call length, the length of the wire. Why does this make sense? Well, when you think about it, as a cross-sectional area or thickness of the wire increases, there is more room for the charge carriers, that is the electrons, to be able to move from one end of the wire to the other. Okay, there's more potential pathways for those electrons to take in a thin wire than in a thin wire. As we'll find out, when you look at a very thin wire, like the filament of a light bulb itself, The filament of an incandescent bulb is designed to be extremely thin in order to provide a really high electrical resistance so that it heats so much, the temperature increases so much that it can actually emit light. So we see that thick wires produce less resistance and less heat than do thin wires. So let's take a look at how we can kind of show this with not a wire, but a piece of conductive paper in the next slide.
We're going to start by taking a look at two factors that affect the electrical resistance of a wire. Now, as you see here in front of me, I have a piece of wire, and I've got this little device here, which is an ohm meter, which can directly measure how much resistance is in that wire. The problem we have with using typical wire is that the resistance is so low. Remember that good wire has low resistance. We want it to be an excellent conductor. That when I actually put the leads of my ohm meter to it, you will see that we get no known or no measurable resistance in the wire because it's such a good conductor. So to be able to do this demonstration, we're going to replace the wire with some pieces of conductive paper here which have a much higher resistance, a more measurable resistance. The first factor we're going to take a look at is the relationship between the length of the wire and the resistance of the wire. And it turns out there's a direct relationship, as I'll show you. So what we're going to do here is we're going to take a look at a piece of wire. I'll use this middle wire here, and I'm going to put the black lead of my ohm meter at one end, and I'm going to put the red lead at some distance away from the black lead, and I'll gradually increase that. So we'll measure the resistance across increasingly bigger segments of wire, and we'll see what happens to the resistance. So when I put my red lead a couple centimeters away, we get a resistance here of about 75 ohms. If I were to move that red lead about twice as far away, notice that the resistance roughly doubles. It's about 130 ohms. If I double that, okay, here we have a resistance, well, of about 230 ohms, and all the way at the end, okay, our resistance goes up to about 375 ohms. So here you see the direct relationship between the length of the wire and the resistance of the wire. As the length gets bigger, the resistance increases. Now, the second relationship we're going to take a look at is the relationship between the cross-sectional area of a wire. You can think of that as the thickness of a wire and the resistance. So what we're going to do here is we're going to look at these three segments of conductive paper, wire, so to speak, and they're all the same length, but notice that each piece has a different cross-sectional area. So what we'll notice is that when we start with a large cross-sectional area, okay, we're going to get a low resistance. There's an inverse relationship between resistance and cross-sectional area. So I'll put the leads of my DMM across this thick piece of wire, and we have a resistance of about 130 ohms. If I put my leads across the same length of wire but a thinner piece of wire, notice that the resistance here increases to about 360 ohms. And if I look at this very thin piece of wire over here, the resistance goes up to nearly 1,000 ohms. Okay, well, 870 ohms. So there we have an inverse relationship between resistance and thickness. As the wire gets thicker, the resistance goes down, and vice versa.
So in this slide, we'll take a look at two more factors that affect the electrical resistance in a wire. Okay, the first being one that we introduced previously, that of resistivity. So as we've already said, the resistivity, okay, is directly related to the resistance. The difference between the two quantities being that resistivity is an intensive property, okay, depends upon only the type of material, okay, not the size or shape of the actual sample of material that you have. And as we said, some materials those mobile charge carriers are more free to move. What makes a conductor a good conductor is that those electrons, which are the mobile charge carriers for metallic conductors, they can move much more easy, meaning they have a lower resistance, where for good insulators, materials we consider to be good electrical insulators, those electrons are much more restricted. They cannot move nearly as easily, meaning that there is a higher resistance. The very last factor that affects the electrical resistance in a wire is the temperature itself. And it turns out that there's a direct relationship. We'll check out a demo of this in the next slide. To try to explain this, well, remember what temperature measures on a microscopic level. Temperature is a measure of particle motion. And when a conductor is at a higher temperature, all of the particles in that conductor are going to be moving faster. Because we're talking about solids for metal conductors, the metallic nuclei now are going to be vibrating much faster than they would be at a lower temperature. The metallic nuclei, remember, this is what causes the obstruction to charge flow, the obstruction to those mobile electrons trying to move past them. The more motion they have, the more obstruction there is to charge flow, the higher resistance. In addition, those electrons themselves, the mobile charge carriers, are also moving faster, but not in any preferential direction, in a random direction. So this certainly doesn't help, even though they're moving faster. It doesn't actually increase the current and lower the resistance in any way if the increased motion is random thermal motion only.
Now, one of the factors that affects the electrical resistance is temperature. And it turns out that as the temperature of a material increases, so does the electrical resistance. If we look at our microscopic model, or we look at this from a microscopic perspective, what causes electrical resistance in the first place is the motion of those metallic nuclei that are getting in the way of those electrons trying to move through the material. So it makes sense is that as the temperature increases and we increase the kinetic energy of those nuclei, well, we're going to increase our electrical resistance. I'm going to try to show this to you with our magnetic ring launcher and ring. This ring right now is at room temperature, and it has a certain amount of resistance being at that temperature. And what we're going to do is I'm going to stick the ring on a ring launcher, and when we talk about electromagnetic induction later in the course, this will make a little more sense, but by having a changing magnetic field through this ring, we're going to induce a current in the ring. And that current that we create in the ring will depend on how much resistance there is in the ring. And the amount of current and resistance will also affect the magnetic repulsion of the ring and ultimately how high the ring goes. So let me show you here with our ring and our launcher. You'll notice that at this temperature, this amount of resistance and the amount of current that we can create with that amount of resistance, our ring will go to a certain height. Oh, better plug it in. That our ring will go to a certain height. Okay? What we're going to do is we are going to now cool this ring down. I'm going to take some liquid nitrogen here, and we're going to cool this ring down to a much lower temperature. So we're going to greatly reduce the amount of electrical resistance in this ring at this lower temperature. And we're going to repeat the experiment. Let me give a little bit of time to cool down. And what we should find is that with this ring at a lower temperature, a lower amount of resistance, we should be able to get a greater current in the ring, a greater magnetic repulsion, and a greater height. So here we go. Let's try this one more time. Take a look at how high it goes. So high it hit the ceiling. We need a bigger classroom. So we see here the relationship between electrical resistance and temperature. Lower temperature, lower resistance.
All right, so I'm going to provide you with an analogy which may or may not help you remember some of these factors that affect the electrical resistance in a wire. Okay, and let's consider the electrical resistance in a wire being analogous to you, okay, being in a crowded theater, okay, when a fire exists in that theater. What sorts of factors will affect your ability to get out of that crowded theater in a timely manner? Let's take a look at a layout of a theater. Now, if we're taking a look at this theater and you exist, let's say, at one end of the theater, and there is only one exit door that is open in the theater, then certainly you can see how the length of the theater, okay, is going to affect your ability to get out in time. Okay, the longer the theater, the more bodies there are in front of you, the greater obstruction there is going to be to people flow. In the same way, if you were a charge carrier, the longer the wire, the greater the number of metallic nuclei in front of you, okay, the greater amount of obstruction there is going to be to you, the charge, being able to move from one end of the wire to the other. Now, when it comes to cross-sectional area, we can see that that is analogous to the number of side exit doors that are open. In the case I have shown right here, if there's only one exit door open, so that we have a very small cross-sectional area, okay, that's going to greatly restrict your ability to get out of the theater in a timely fashion. But as we start to open more and more of these side exit doors, okay, there becomes more and more pathways for exiting the theater. Okay, and it's going to make it a lot easier for you, the charge carrier, to be able to get out of the theater in a quicker fashion. When it comes to resistivity, remember that resistivity is a property of the medium itself. So let's consider the difference between being in a crowded theater full of young people versus being in a crowded theater full of old people. In a crowded theater full of old people who move much slower, okay, it is going to take you a lot longer to get out of that theater, okay, than if you were in a theater with young people who could move much quicker. And finally, we can think of temperature as being analogous to panic. What happens when people panic? When people panic, their motion increases, okay, but not in any preferred direction. Okay, so in that sense, that is going to greatly obstruct your ability to be able to get out of that theater. Rather than people filing out in an orderly fashion, okay, allowing for a quick exit, when people run like chickens with their head cut off randomly in all sorts of directions, okay, that is going to increase the amount of obstruction there is to you being able to get out of that crowded, burning theater in a timely fashion.
So of these four factors affecting electrical resistance that we introduced in the previous slide, it turns out that we can relate 3 out of 4 of these, okay, to the resistance in a very simple empirical formula, okay, as such. We say that the resistance goes like the resistivity times the length divided by the cross-sectional area. And you see here that this expression shows all 3 of those relationships. The resistance is directly proportional to the resistivity, directly proportional to the length, inversely proportional to the cross-sectional area. So when it comes to temperature, we'll see in a future slide, okay, the next slide I believe, how we can quantitatively express the relationship between resistance and temperature. Okay, so let's take a look at a simple example here, okay, just involving these 3 factors. And in this example here, we're given 3 different cylindrical copper conductors. Okay, the first conductor, the conductor on the left, has a length L, cross-sectional area A. The middle conductor is longer. It's 1.5 times as long, okay, but it has only half the cross-sectional area. And the conductor on the right-hand side, okay, again, has only half the cross-sectional area as the first one, okay, and has half the length of the first one. So we're asked how the resistances of each of these 3 conductors compares. Well, let's use our formula and do the calculation. For the conductor on the left, okay, the resistance is simply the resistivity rho for copper times the length, which is given to us L, divided by the area, which is given to us as A. Okay, for the middle conductor, okay, when we've got the same resistivity, remember, copper at a given temperature has a specific value for resistivity. These are all copper conductors. They all have the same resistivity. Okay, when we plug in our expression for length, okay, 1.5 times L or 3/2 times L, okay, A over 2 for a cross-sectional area, and we do the simplification here, okay, we find out that the resistance can be written in a simplified form as 3 times rho L over A. Notice then that the middle conductor has 3 times the resistance of the conductor on the left. Okay, why? Well, it's longer, okay, increased length means it's increased resistance, and it's thinner. Okay, smaller cross-sectional area, that also increases the resistance. The conductor on the end, okay, the right-hand conductor, when we plug our values in there, okay, same value for resistivity, half the length, half the cross-sectional area. You see there that we get exactly the same resistance for that conductor. Okay, so even though it's only half as long, it is also, which would decrease the resistance, it's also half as, okay, has half the cross-sectional area, okay, which would decrease the resistance in the same ratio. So it turns out that a resistor is nothing more than a piece of conducting material that is designed to have a specific value of resistance. So in circuits, and this is something that we'll talk about in our next lesson, we can use resistors to control, okay, the current in a circuit. Certainly if you want to have a certain amount of current, okay, then by putting a resistor in there of known value, you have a certain amount of obstruction of charge flow. And this will nicely allow you to control the current in the circuit, okay, because the amount of current required to run whatever circuit elements are in that circuit. So what you see in the upper right-hand portion of your screen here, these are examples of resistors. You'll notice that they have this characteristic color coding to them. And if you've ever opened up a piece of electronics equipment, you know, a radio, whatever, okay, you will most likely see one of these brightly colored resistors inside. So resistors can be used to control the amount of current in an electric circuit. They can also be used to convert electrical energy into heat. So when you're looking at an appliance containing a heating element, okay, whether an electric stove, oven, okay, or a coffee maker, these are nothing more than electrical resistors, okay, that are designed to have a certain amount of resistance in order to convert electrical energy, okay, in your circuit into thermal energy. You know, very often thermal energy production is an unwanted byproduct of current and resistance in circuits, but sometimes you actually want to use a resistor in the form of a heating element, okay, to produce heat. So we will use a circuit symbol to represent a resistor in a circuit, and it looks like this. And you know, don't ask me why, okay, but that is a symbol, not too hard to draw, that represents a resistor in a circuit. And we'll be talking about circuits, okay, very shortly in this course. So what you see on this slide is a color chart that is used to identify, in this case, a 4-band resistor. Just so you know, there are 5-band and 6-band resistors that exist as well. So when you take a look at the last band of the resistor, the one furthest to the right, okay, that indicates a measurement of the tolerance, which tells us the range of accuracy you would expect for your resistor. So as you might expect, the smaller the tolerance, the more accurate the resistor, and of course, the more expensive that resistor will be to purchase. The second to last band will serve as a multiplier. That is a power of 10. The other colored bands, okay, the first 2 in a 4-band resistor, the first 3 in a 5-band resistor, and the first 4 in a 6-band resistor, these bands will represent the numbers to be multiplied. So, for example, for the resistor you see pictured on this slide, which is a 4-band resistor, we take the first 2 colors, okay, the green band and the black band, okay, and when you look, the green band represents the number 5, the black band the number 0, so those 2 bands in tandem give us the number 50. Remember, the third band, which is red, is the multiplier. When you look at the color chart, the multiplier here for red is the number 100. So when you take 50 times 100, you get the number 5,000. That tells us that this is a 5,000 ohm resistor. Okay, the last band represents the tolerance. So in our chart, the brown band represents a tolerance of 2%. Somebody paid a pretty penny for this resistor. In a previous slide, we talked about the various factors that affect the electrical resistance in a wire, namely the length of the wire, the cross-sectional area of the wire, as well as the resistivity of the wire. But we didn't talk about the effect of temperature upon, okay, both resistance and resistivity. So that is what we're going to take a look at now. And it turns out there is an empirical law that relates the resistivity of a material, okay, to temperature. And it looks something like this. So let's take a look. What do these symbols represent in this empirical law? Well, rho, as we would expect, that represents the resistivity, okay, of your material at a temperature T. Okay, remember that resistivity is an intensive property of matter. Okay, it does not depend upon the sample size. Okay, rho naught, that represents the resistivity of your material at some reference temperature T naught. And this can be looked up in a table. And alpha is what we call the temperature coefficient of resistivity. Again, this is a property of the material itself. And this too, this resistivity coefficient, okay, this temperature coefficient can be looked up in a table as well. So to get a little bit of practice applying this empirical law, let's take a look at an example here. And we are told in this example that a common flashlight bulb is rated at 0.3 amps and 2.9 volts. And these are the values of the current and voltage under operating conditions. Okay, so for example, a 3-volt bulb, a 3-volt bulb and a 3-volt battery, okay, you can have two 1.5 volt batteries in tandem to give you a total voltage of 3 volts. But when it's actually operating, that is when you actually have a current in your circuit, as we will find out, the actual voltage, the operating voltage, is going to drop slightly, okay, in this case from 3 volts down to 2.9 volts. And for when the flashlight bulb actually has a current in it, there's a certain amount of resistance. Now, given the operating voltage and current, we could figure out what that resistance is using Ohm's law. Okay, we have not talked about that yet. We will very shortly. So to be able to do this problem, and by the way, Ohm's law will tell us what the resistance would be, okay, under these operating conditions. But I'm just going to give the value to you. It's 9.7 ohms, okay, since we have not yet talked about Ohm's law. We will shortly, though. So we're told that if the resistance of the bulb filament at room temperature, that is 20 degrees Celsius, is 1.1 ohms, what is the temperature of the filament when the bulb is on, okay, when it is at its operating temperature? We're going to assume that the filament is composed of tungsten. So we are going to start by revisiting this fact here that factors that affect the resistance of a wire, okay, the resistance is directly proportional to resistivity, length, and inversely proportional to the cross-sectional area, okay, for a given resistor. What I want you to notice, though, is that if you're talking about a specific given resistor, that resistor has a fixed length and cross-sectional area, okay, in which case, when we take this ratio of resistance at the operating temperature to the resistance at the reference temperature, R over R naught, okay, this is the same ratio of resistivities, okay, at the operating temperature compared to reference temperature. And this is so because, like we said, for a specific resistor, which we have in this tungsten filament here, okay, the length and cross-sectional area will be the same. So end result ratio of these resistances at operating versus reference temperature will be the same as the ratio of resistivities. We're given the resistance values here, so we know that resistance ratio as well as the resistivity ratio. Okay, given that, we're going to take our empirical law right here. We are really given all the information here except for T, that is the temperature of this tungsten filament at its operating temperature. Okay, the other values are given to us. So basically, we now just have an algebra problem. We've got to solve this empirical law for T. So we'll do this in a couple steps here. First thing we're going to do is we're going to divide both sides of the equation by rho naught and subtract a 1 from both sides. That's what I'm doing in this first step. Okay, in the next step, we will divide both sides by alpha and add a T naught to both sides, in which case we've met our objective. We solved this empirical law for T, the operating temperature. All we have to do now is to basically plug in these numbers. Okay, remember alpha over here. Okay, this value is given to us in the table for tungsten here, 0.0045 in SI units here. Okay, this ratio of resistivities at operating temperature to reference temperature here, we said is the same as for resistances, so we've got that ratio. We subtract a 1. Okay, we add T naught, the reference temperature here, which we get from our table is 20 degrees Celsius. Okay, so given that, we plug this all in, we do the number crunching, and we come up with this value for the temperature of that filament at its operating temperature. I hope you realize that that is really, really high. Okay, that filament is extremely hot. Okay, and it must be the case. This is why we said in order to produce light, a filament must be extremely thin so that it has a high value of resistance in order for its temperature to get to be high enough so that it actually will emit light. And when these light bulbs, the incandescent light bulbs, were initially being created by Thomas Edison, it was a real problem to be able to find a material that you could make thin enough and get it a high enough temperature, okay, where the filament would not actually break apart. Okay, it turns out that tungsten was the appropriate material. Okay, it has a certain expansion coefficient that was also acceptable to be able to construct a thin filament that could reach a high temperature without actually breaking.
And the last topic that we'll talk about in this video, really a huge topic that we will just barely touch upon, is that of superconductors or superconductivity. So let's start by defining what exactly we mean by a superconductor. A superconductor is a type of material that becomes a perfect conductor, that is, having no resistivity, or said alternatively, an infinite conductivity for temperatures less than some critical temperature we'll call T sub C. Now, there was a model to explain superconductivity, okay, called BCS theory, named after the founders, Bardeen, Cooper, and Schrieffer. And this model, it is a quantum mechanical model, okay, that involves electron pairing, okay, which results in a lowering of the energy state, okay, of the system. And this lowering of the energy state allows electrons to move through the crystal lattice when they pair up. Okay, they call these Cooper pairs, with virtually no energy loss to the metallic ions, so virtually no resistance. And this quantum mechanical phenomenon, as with many, can be explained when we take a look at causality in nature, you know, why things happen, what is the impetus for things to happen. Very often we find out that things happen because of a lowering in the energy state of the system. Now, superconductors had been known since 1911. Okay, and from that time until about the mid-1980s, okay, there were thousands of superconducting compounds that were known, okay, that have been observed for very low critical temperatures. Basically, most metals become superconducting when you bring them down to a low enough temperature. That is about 4 degrees above absolute zero. So while many materials become superconductors, they're not really practical because it takes a lot of energy and a lot of money to reach temperatures of about 4 Kelvin. But what happened in the mid-1980s, and I can vouch for this because I was alive for the superconductor revolution, is that there was this class of copper oxide compounds discovered with relatively high critical temperatures on the order of about 100 Kelvin. And if you think about it, liquid nitrogen will boil at a temperature of about 100 Kelvin. So all of a sudden, liquid nitrogen is very inexpensive to manufacture since the air is, you know, about 78% nitrogen. So all of a sudden, superconductivity became a practical, technological reality in the mid-1980s. There was one very limiting factor, though, okay, and that is the fact that this class of copper oxide compounds are very brittle. Unlike most metals, which are very malleable and can be drawn out into thin wires, okay, malleable and ductile, okay, these compounds that could become superconducting at relatively high temperatures were very brittle, and that made them very impractical for widespread use in technology. But let's take a look at some of the properties or applications of superconductors. So the most obvious property, okay, and comes from the name, is that superconductors have virtually no electrical resistance. So a high temperature superconducting wire to be used in supercomputing miniaturization process. This is actually used today. That the problem with supercomputing is that when you cram too many conventional wires into a small space, it generates a lot of heat because of the resistance. But if you're using superconducting wires that have no resistance, you don't have that problem. So you can cram a lot of superconducting wires into a small space, okay, with no heat being generated. And this is talked about being used in power transmission as well. We said that roughly 40% of the energy that gets transmitted from the power station to your neighborhood gets lost in the form of heat. Okay, but you can imagine that if we could transmit power in superconducting lines, there would be, we would be saving about 40% of that energy. Supercurrents, currents existing for years in the absence of a potential difference. So without any electrical resistance, we can, produce a current with a given voltage, that will exist, even when the source of that current is no longer there. So this is used in today's technology. Okay, very powerful electromagnets used in medical imaging, okay, like MRI machines make use of these superconducting magnets. And the Meissner effect, okay, this is a property of superconductors that we will talk later on in the course. We will try to explain when we talk about electromagnetic induction, but they have this very strange property that superconductors repel magnetic fields. The magnetic flux is zero inside a superconductor, thus allowing superconductors to repel magnetic fields. And in some of the applications we talk about later, we can talk about zero friction mechanical devices like maglev transportation, okay, where you may have a superconducting track that can repel a superconducting train, okay, in a virtually friction-free environment that could allow very high transmission speeds.
Now, superconductors are perfect conductors. They offer virtually no electrical resistance, so electrons can move through superconductors unimpeded with no resistance. Superconductors also have this very interesting property that they repel magnetic fields. It's called the Meissner effect. And what I'm going to show you here is a superconductor. This is a special ceramic material that is superconducting at a fairly high temperature, the temperature at which liquid nitrogen boils. So I'm going to stick this superconducting disk in a petri dish here, and I should say it's not a superconductor yet because we have to bring it down to a low temperature. I'm going to pour some liquid nitrogen on this to cool it down. Liquid nitrogen has a boiling point of almost negative 200 degrees Celsius. And what I'm going to do is I'm going to place a little tiny magnet on top of the superconducting disk, and you will see that right now it's not superconducting. Okay, up right here we've entered a superconducting state, and you'll notice that the superconductor has this property that repels magnetic fields, and it's repelling this magnet. You'll notice that this magnet is levitating above the superconductor. No contact is made, and that's why I'm able to freely spin it.